Our first speaker in this track is Frank Corrigan. So I'm going to be speaking about scenario planning with data on steroids. So with an economics and business development background, Frank builds and leads data teams that excel in data decision-centric analytics. His curiosity implores him to continuously learn with his team members and challenge them to build model thinking with technical, scalable solutions. Thank you, Frank, for being here. We're super excited to hear your talk.
Thanks for the intro, Christina. Can I get a check really quick? Can everyone see my screen? That says scenario planning with data on steroids. Okay, thank you. So as Christina mentioned, my name is Frank Corrigan. I'm a director at Target. I run a group that I call Decision Intelligence, which uses data and analytics to help decision-making in supply chain. This talk is called Scenario Planning with Data on Steroids. In the book, Great by Choice, Jim Collins starts out by reminding us that there is no new normal. There's only ever instability, disruption, and change. So with that, the best leaders he describes are continuously planning for multiple futures and hedging accordingly. Now, in scenario planning, there's an abundance of mental models that you can use to assist how you think about the future. Some of those are premortems, backcasting, and game theory. But perhaps to me, the most data-driven of all of those is this tool called Monte Carlo simulation. It is a process where you use a ton of data to give you different perspectives about what the future might look like. So to me, it is really scenario planning with data, but on steroids. In 2020 and into 2021, the COVID-19 pandemic wreaked havoc on supply chains. There was disruption everywhere. And it started in 2020, but as Dr. Price just showed us, it is continuing to this day in 2021. In retail, it has disrupted purchase patterns and really constrained labor capacity, either at warehouses or on truck routes along between those different nodes. At the ports of LA Long Beach in particular, where the US imports $300 billion of consumer goods and materials annually, they've had major labor constraints. So they've seen a big backlog of container ships outside of the port. Typically, in normal times, there are 0 ships waiting in the water to be worked at that port. Over the past year, that number has grown. And earlier this month, in mid-September, the number of ships waiting to dock, waiting outside in the water to dock at the port was over 70 ships. That's hundreds of thousands of container ships just waiting out there. You've probably seen the impact at retail stores like CVS or Target, where the shelves seem emptier than normal, they are, or in headlines where car manufacturers are halting assembly lines because they can't get component pieces. If you are planning within that supply chain, perhaps at a warehouse, you want all of the perspective and insight you could get to how these delays at the port may impact what's going to arrive at your warehouse. We can build a lot of data-driven what ifs with scenario planning using Monte Carlo simulation, and we can do that in R. I'm going to break the rest of this talk up into 3 chapters. So first, I'm going to use the remainder of this deck to flesh out a framework and how to think about Monte Carlo simulation. Then I'll hop over to our Markdown file where I'll walk through an implementation. And then finally, I'll give you some ideas for how to deliver this to stakeholders in Shiny. Now, simulation to me is just as much a mental model and how you think about it as it is a computational analysis. For Monte Carlo, that means A, you really need to understand the system flow. What is the code trying to represent? And B, you need to understand in all of those components in that system, what does the variability look like? And finally, C, you need to build out a framework for repeatedly simulating that system flow. We can't move forward without really understanding that system flow. So let's start there. In this demo, we have 10 order points that are associated with an origin port. So we order from all of these green dots. They will flow through an overseas origin. So you can think China, you can think Vietnam, you can think locations in Europe, and they will flow across the ocean on container ships and arrive at the port of LA Long Beach. This is where that delay is happening that I was referring to earlier. finally, after they finally get through the ports, they'll flow to a domestic warehouse somewhere in the continental US. This is the idea for what the system looks like. And you can see we have 3 transits, which we'll be focusing on. So order to origin port, I'll also call this overseas port, origin port to domestic port, and then finally domestic port to domestic warehouse. Now, let me plant the seed here. There's always this trade-off between complexity and usefulness. Obviously, this model right here is not exactly what reality looked like. It is a simplification of reality. But with these simulations, there's always a trade-off between how granular and representative of reality you are against the usefulness for a decision maker. Because if you put a spaghetti chart on this screen and show the decision maker, this is how everything flows around. Do you get it? They're going to say no. But there's also a trade-off between the complexity of the simulation model and the ability to maintain it. And I'll mention this again later as we go through the implementation piece. The second part of this is understanding the variability of each of the components. So I mentioned those transits, and each of those transits, those 3 transits, have variability involved in them. As ships come across the water, it's not like they always make it in 14 days. There might be, 14 days with some variability around that. Now, a lot of planning, in scenario planning, participants use or agents use averages. And using averages for planning is okay in supply chain if all of your distributions from your ordering volumes to your transits are normally distributed like this. Some things will wash out, or these things will wash out with the things over here. But the truth is, in supply chain, most of our distributions are not normally distributed, especially with the transit. So they're more skewed and they look more like this. And it makes sense because if this is your average here, where I'm scrolling up and down, it makes sense for things to be able to arrive much later than average when things get delayed at some point, order didn't get picked up, or a container didn't make it onto a ship. But it's hard typically for things to be much earlier than average. So a lot of our distributions end up looking like this. And if you're using the middle, there's going to be a lot of stuff here that you're missing, and you're going to get these volume swings at some point in your supply chain that are unexplainable because you assume that all the distributions look like this. Now, the trick here will be that we want to sample these distributions, and we'll want to do that in a sequence to arrive at what I'll call an outcome distribution. So you string a bunch of these together, and ultimately you get to a distribution of how much volume is going to arrive at the end. Let's look at one of those sequences. Recall that I had 3 transits in our quote unquote supply chain, right? Our simplified supply chain. So in that first leg, our order to overseas port, maybe the average of our distribution is 14 days. And in the second leg, maybe our average is 14 days again. And then the third leg, 4 days. If you sum up those transits, that's 32, right? If you're a retail company or running a supply chain, great, like the transit is 32, let's go with that. And we'll just assume everything flows at 32 days. Well, the truth is, if you sample these distributions, whether it's normal or non-normal, more often than not, when you pull an individual value out of them, you're not going to get a 14 or a 14 or a 4, right? You're going to get something different. So when I think of this, I think, well, in a single instance, what if I sample a single value? What is the total transit I'm going to get? I might sample 14, which is the same as my average. I might sample 14 again. And then on my third transit, I might sample 5. So my red line here is a little bit longer than my average. If I was crazy about the visualization here, these things would overlap, but then you'd only be able to see one bar, right? But the truth is, in this single instance where I sample these 3 distributions, I get a total transit of 33 days, which is only one away from the sum of some of the different transits. But if I did it again and I had a second instance, I might sample 20 days, 16 days, and 4 days. And that gives me a total transit of 40. That's 8 days longer than our 32. And this is important because if you're planning by weeks, imagine you're planning your inbound volume by week. Now, this transit pushes your volume to a different week. It pushes you outside of your planning window. And that's why it's important to remember. If we did a third instance, we might get sample values of 16 days, 14 days, and 4 days, giving us a total transit of 34 days. Now, the most important thing to remember here is that if we did this again and again and again and again, we might end up with an average of these averages around 32, but now we start to get a sense of an outcome distribution. What are the different possibilities that we might see, and what are those different transits? And that's what we'll continue on here. So the third part of this is, if we think about the framework, it really helps if we start to describe what our output data would look like. So even before coding, if you kind of have a visualization of what the data might look like, it becomes helpful. And we can describe that data right at the start. So number one, if this is our representation of our instance, we have a sequence of order dates. I called it date range in the column, but these are order dates. And associated with each order date, we have an order volume. And then we sample our transits for each of those three legs. And then we have a full transit here by summing up the individual sample transits. We add 32 to our order date to get an arrival date at your domestic warehouse of January 2nd. So remember, we're trying to help the warehouse plan for all the possibilities around how these port disruptions are going to disrupt their inbound volume. It's really powerful if you can describe a single row of data, whatever data you're using. Hopefully it's not 200 columns long, but right, in this case, it's simple enough to be able to describe it. So if we order on December 1st, 1,002 units, and it takes 12.8 days to get from order to overseas port, and takes 15.5 days to get from overseas port to domestic port. And then it takes 3.7 days to get from domestic port to the domestic warehouse. Yeah, our full transit is going to be rounded 32 days, which means if we ordered on December 1st, it's going to arrive on January 2nd. I know that seems simple, but being able to articulate a row of your data sometimes leads you to find things that are obvious, but you miss them for whatever reason. The next step, after we're able to describe that single instance, right? We did the sampling, we can describe the single instance, would be to think about what is arriving at my domestic warehouse. So we can group by the domestic warehouse arrival date and add up your order volume. So for instance, on January 4th, we received these two order volumes of 999 and 999. You group that up to come down here, and you have two columns, and on January 4th, 999 plus 999 is 1998. And you start to see the possibilities on the different days. This is only one instance. What if we did it again? Would we get the same values? Well, the answer is no, because we're sampling, right? So every time we sample, we're going to get different values here. But if we did it again and again and again, remember, we're looking for that outcome distribution, and we'd start to understand that, oh, there's a range of possibilities for what might arrive at my warehouse. And if we look at that quite simply, here's that single instance from the prior screen where on January 4th, we received 1998. But if we did it again, we might be receiving 0 units on January 4th. And if we did it again, we might be receiving 1,002 units on January 4th. Now imagine doing this 10 times, 1,000 times, 10,000 times. You would start to have your own curve of what we think is going to arrive on January 4th. If we thought about that framework within a process chart, a flow chart context, this is what it might look like. We would start with that single instance where we're feeding the distributions in to get that first data frame. And then we need to aggregate it up to the arrival date. And that's what we did here. And then you want to add that to a master data frame, right? We have a holder master data frame. Let's hold it and add in our instance. And then we go again, right? We have a single instance, fed distributions. We aggregate it up, add it to the master data frame, so on and so forth. Let's imagine we do that 10 times, and after 10 times, then we have an outcome distribution. So for a single arrival day, January 6th, we have multiple observations here. In this on the screen here, we on three of these instances for January 6th, we received 0 units, but on 2 of the days we received 1999. Now, if we did this 100 times, you'd have more variety of values and start to look more like a continuous distribution. What we have, when you have a continuous distribution, you can start plotting stuff like a box plot, where you can see, yeah, most of my stuff is most of my arrival volumes are between 750 and 1250 here. But if I have a 1,500 unit arrival day, it's not out of the question. Even if I have a 2,000 unit arrival day, it's probably a 1 to 2% chance, but it's not an impossibility. So you taking the idea of this outcome distribution, we probably want to think of a use case, because every time we do any kind of modeling, we always want to be able to think about how do we put it into practice and how do we make it useful. And a real quick demonstration before we hop into the idea of scenario planning around those port delays is if you have an arrival distribution where your average is 1,000 and your standard deviation is 2,000, you can feed that into, right, this is super basic, but you pull up a spreadsheet and you feed it into your arrival volume, especially if you're just portraying this as a proof of concept for a potential user. Then you can see over this, almost 2-week period, you have arrival volume of 967, 999, 1,082, and it all hovers around that mean of 1,000. So if you look at your average, you have 1,000. Some of your days are big and some of your days are relatively small. But how does this become useful? Well, if you're a warehouse planning for arrival volume and you want to understand, will you be able to work all of that volume? You can say, I'm going to establish a labor plan of processing 1,000 units a day. Typically, these stay pretty consistent because in terms of hiring people and getting people to come work, consistency is usually better for people than inconsistency and not knowing if they're going to have work tomorrow. In some states in the US, this is actually, there's laws that mandate this. But let's say we're consistent with processing 1,000, then you could figure out over this 2-week period, and then obviously over the few month period ahead of you, you could start to understand, will I be carrying backlog? Will I be able to process my volume? So on this first day, January 6th, you had 967 units come in. You had a processing power of 1,000, no backlog, right? So this is unit backlog, and this is in terms of days of backlog. We're at 0. Same thing happens on January 7th, but on January 8th, now 1,082 units came to your warehouse. You could only process 1,000, and now you have backlog. And this becomes really important when you get those high spike days. So for instance, January 12th, if you have 1,550 units arriving at your warehouse and you plan for 1,000 to be worked, you're going to have a pretty high unit backlog and a pretty high days of backlog here. How long is that going to take to get through your warehouse? Well, so long as, right, you don't have multiple days where your volume got elevated, and we'll see this when we do scenario planning later, that's a possibility. But if your volume is pretty normally distributed across time, you'll be able to work that down over the next few days, coming down to 0.2 days of backlog here, and then ultimately working it back down to 0. Now, if the cost of a delay, right, if you want to get everything through your supply chain in your warehouse fast, because the cost of not having it at the end of your supply chain is very, very high, and I'll relate this back to what Dr. Price was talking about, right? The cost of not having something at the end of your supply chain is very high. You likely want to plan conservatively and raise this number to 1,050 or 1,150. You will have excess labor in your warehouse over time that is perhaps standing idle, but you will, because there is uncertainty in your supply chain, which we can't reduce, you will reduce the prospect of having backlog and getting stuff backed up at your warehouse. So we're not at scenarios yet, but you can already see how the model becomes useful. We sample a sequence of non-normal distributions to get an output distribution. That is the range and spread of what might arrive at our warehouse. And then you could start to plan, how quickly do I need to get things through my warehouse? How many people do I need? How long do I have to run my warehouse? Let's look at an implementation. I'm going to switch over to that R Markdown document. And what I've created here is pretty wordy. So there's a lot here because everyone will have access to the code and they'll be able to see this if they want to venture and run it themselves, or hopefully try out some of this stuff on their own problems. But for this talk, what I'm going to focus on are just the mainest points highlighted in yellow. I'll start with distributions because, as I said before, distributions are the building blocks of Monte Carlo simulation. One of the probably the most important part of this is being able to create distributions and then sample from them. I think one of the most well-known sampling functions is the rnorm function, which allows us to sample from a normal distribution with a given mean and a given standard deviation. So right here, the first thing we do in this R Markdown is say, I want one value pulled from a distribution with a mean of 14 and a standard deviation of 2. And when I run this, it returns to me a vector with just one value, that's 14.9. Now, if I did it again, maybe the value would be 15.2. And if I did it again, maybe it would be 16.3. But if you imagine that normal distribution, we're going to pull a single value, just one value, and return it. But one value is not going to do do much for us. It's good to test this out to understand how it works. One value is not going to help us much. If instead we pulled 10,000 values, now we would have a very long vector and we could plot that. And if we plotted it in a histogram, you would get what, looks like a normal distribution, right? With your 14 in the middle, and then you have a spread around your value of 14. So this is good. Normal distributions are one of the most common and I think well-known types of distributions, but we don't want normal distributions. Remember, we're in supply chain. Most of our distributions are non-normal. What I want is a right tail distribution because I want to represent transits. And in my experience, what I've used for these right-tailed non-normal distributions is the fgarch package, because they have this really beautiful function called rs norm, which operates very similar to the R norm function. I can pull 10,000 values. I can feed it a mean of 14, and I can feed it a standard deviation of 2. But then I have this parameter xi that helps me control the length of the tail. And as I scroll down, you can see that it helps me to create this right skew distribution where I have a tail going out to 20, 25. So I imagine this being transits. And if I thought that my transit was even more volatile and things were even later, I could make this value up here 3.5 or 4.5, and it would stretch out my tail to 30, maybe a value of 40. What I know in my experience about ocean transits, and there's plenty of stuff online that you can go read, but this felt about right, where your average is 14, and then you have this longer tail where you have some stuff coming from around the world that takes a bit longer. So if you do this in real life, it is, as you can see, I'm making distributions up based upon my domain knowledge and my domain experience. But if you do this in quote unquote real life, you definitely want to make sure that you are pulling the data from your own business, assuming that you have access to that and it exists, and then examine what the distributions look like and then fit to those distributions. I don't go deep into that here, but if we want to talk about that offline, reach out to me and I can point you in the right direction on that. We want to start with a single instance. So just like we looked at the framework in the slides, we want to start with a single instance. And I don't know about you, but I think it is really healthy when possible to start with the most basic and do it manually, so I can mess around with the parameters and I can mess around with the input. So here's the code, but let me guide your eyes down here first, and then I'll walk you through. Remember, we looked at this table, a single instance, and I described your first row of data. This is what I'm trying to create with this manual block of code up here. I create a date range, which is a proxy for my order dates. And I just use the seek.date function between December 1st and March 1st, and I want it by day. At first, I only want to look at a single port, right? So remember, in the framework, we want 10 overseas ports, but here I'm going to start with 1 because I want to start simple, I want to start easy, and then I'll build from there. So I start with a single port and then I flow. So I have my first column, now I need the rest. What I've done here is for my order volume, I have used the R norm function. So I'm saying my orders are normally distributed. So the amount we order is going to be 1,000 units with a standard deviation of 1. And the length of the vector I want, obviously I want it to match how many order dates I have. So every order date is associated with a volume date. And that's why I use the length of the date range that I specified up here. The other thing to mention is that my standard deviation of 1 is basically nothing, right? Like I almost have a uniform distribution here. When I first do this and I start simple, I want to try to reduce any of the randomness and the noise. So I could even make this 0.01 so that all of my values are 1,000 because I'm using the round. And that will allow me to say, hey, what I think the code is doing, is it actually doing? So when I'm trying to gut check this and verify that everything is working, reducing the volatility at first seems to be a really helpful recommendation. And then to round out our data frame, we need transits. And you can see I use the rs norm function. I want the number of order dates that we have, right? So each row, we want to sample that many transits. And I use a mean of 14, standard deviation of 2. And based upon what I know, a tail of 2.5 seemed like a good starting point. From there, I can add these 3 transits together to get my full transit, which is right here, and then add my full transit to our order date, what I call date range, to get for this first row, we have an order date of December 1st and an arrival date of December 29th. In all of these, in every step I do, I always try to output what the data frame looks like, but I also try to visualize it in some kind of graph to verify, yes, this looks about right, this looks sensible. And that's exactly what I do here. So I take this table of data, I start with that, I pipe it into a group by warehouse arrival date, and then I sum up my order volume, right? And that's that aggregate part of the function at the top of our flow chart. The only additional thing I do here, which is worth calling out, is using this complete function, because sometimes if we aggregate up in a single instance by warehouse arrival date, you won't have, let's say, January 6th in your data set, right? Just on that date, no volume happened to fall within a single instance. And in which case, I still want that in my data set for when I visualize this stuff, but I want the arrival volume to be 0. So that's what I do here. I complete the date sequence or the order date sequence. And then if there is volume, use the volume. If not, use 0. If we plot it, does it make sense? It does. So if this is a single instance, we have our values floating basically around 1,000. Remember, our order volume is 1,000. If we float it through, we'd assume this to be the arrival volume at the domestic warehouse to float around 1,000. But of course, you're going to have 0 days. You're going to have 2,000 days, 3,000. There's even a day where you're above 5,000 unit receivable. So this gives me a sense that, yeah, okay, I understand exactly, like this was the simple stuff. This was the easy stuff. I got the easy stuff right, which makes me more confident in the harder stuff that we'll pick up later. Before we jump into the multiple instances, I always ask myself, like, hey, I did this. What would I do with this if I was sitting down with a stakeholder today? And the answer is, this wouldn't help me really do anything. I can explain it to a group in our conference, but sitting down with a stakeholder wouldn't be much value, because the real magic here is doing this again and again and again and again, and doing many instances to understand what the realm of possibilities looks like. And before we do that, before we get to that realm of possibilities, I want to wrap exactly what we just did into functions, because that will keep our code organized and it will help me to read and follow everything else later. So those two things that I just did, I wrap in a function. This is nothing new, right? Everything we did manually up top, I do again, except I wrap it into this inner sim function. We have no parameters, but it will allow me to run the inner sim function, save it to a data frame, and then visualize. And it looks, right, nearly exactly as we had above, a little bit different because we're sampling. So there's some randomness in the transit, there's some randomness in the order volume, but looks very similar. And same thing with that aggregation to the domestic warehouse arrival date, so that we can plot all of this stuff, same exact thing as we did above, but now it's just in this function called ag by arrival function. And if we visualize that output, okay, this makes sense. We do have some 0 days for this particular instance, but the output does look sensible to me. And if you go into deeper verification, you would find that it is sensible to you as well. I'll repeat, one instance is sort of useless. We have to do it over and over again. So let's talk about multiple instances. And before I scroll down here, I'm going to take a quick breath and call out that mentally for me, this took a bit of time to grasp, right? The first time somebody ran me through this, I didn't get it. When I went online and tried to read about Monte Carlo simulation and tried a lot of the tutorials out there, if you do the quick Google search, your first page of Google is examples in finance or simulating pi and things like that, which were a bit foreign to me. So I just want to call out that this took me a while to really understand and be able to put together. So if you're seeing this at first glance and it doesn't make sense, I wouldn't get discouraged. Eventually, it becomes a natural thought process, but the truth is it takes practice. Let's bring back that process slash flow diagram that I had on the slides earlier. So if you remember, we had a single instance, we aggregated up, we add to a master data frame. That's what we need to build. And then when we build this, we're getting closer to being able to do scenario planning with all this underlying data. The function, and it becomes relatively short because we created those inner functions up top. But what we have here is, let's start where we're familiar. Start with this, inner sim. Oh yeah, that's the function we created based upon our manual work. This inner sim represents what's going on here. After we create a single instance, the next thing we need to do, remember, is aggregate it. Oh yeah, we created that function for aggregating by arrival date. Yeah, okay, I get what we're doing there. And then finally, oh, that's master data frame. That's what I'm doing here. So this part is all repeat. The only new stuff is that I'm wrapping it in a for loop so I can do it over and over and over again. And on this function, you can see we're doing it 1 through n times. Well, what is n? It's a function of this, it's a parameter of this overall function, and n equals 10. So this inner time, if I drag my mouse around, I'm going to do it 10 times before I want to examine the output distribution. But of course, I can't add to a master data frame if I don't have it. That's why I start the function with declaring a master data frame with just 2 blank columns, domestic warehouse arrival date and domestic arrival volume. But otherwise, right, because we stayed organized up top, your function looks rather clean, rather simple. I will call out myself because some of you are probably thinking of it. There's no comments in here, right? Bad practice, Frank, get some comments in there. I will. But if we test this out, what does it give us? Now we can run this function outer sim. There's no parameters or anything to put in. So test outer sim is what we want to inspect to make sure it looks right. In order to make sure it looks right, I'm going to scale it down a little bit and just look at arrivals on January 10th. Now, of course, we're going to have multiples of these, right? And we do. So January 10th is the domestic warehouse arrival date. And you can see we have a distribution of different possibilities or different arrivals. If you are presenting this to a stakeholder and you are trying to visualize it, you can put a bunch of lines on the screen and that might work. What I have found to resonate with stakeholders, and they almost immediately and intuitively, is a line chart with a ribbon around it. The gray shaded region behind the line, they almost instantaneously realize, oh yeah, that represents the possibilities, that represents the uncertainty. So taking all of this data now, and so for every date in our data frame, we have multiple instances, right? For January 10th, we have an average. For January 10th, we have a 25th percentile, we have a 75th percentile, we have a min and a max, if we calculated that. So that's what I do. And as I scroll down, I'll show you, we can organize the data in such a way to create that chart. So the first thing I'm going to do, I just mentioned, we have a mean for January 10th. We have a 25th percentile, 75th percentile. And that's what I calculate here with our output. That will allow us to create the line chart and the ribbon around it. So as I scroll down, any of you that use ggplot, which I would assume is the majority, is familiar with ggline, and perhaps some of you have also used geom ribbon, which creates the gray band behind your line chart. And all of this together, scrolling down, our chart ends up looking like this, where you have your line chart, which is your mean, which fluctuates around that 1,000 level. You have the gray shade in the background, which represents the bottom is 25th percentile and the top is your 75th percentile. For no particular reason in this case, I decided to use the interquartile range for uncertainty here. Now this looks a little bit broken, or rather there's a lot of cracks in between the days, and that's because we're only doing 10 instances. When we up the number from 10 instances to 100 instances, this will flesh out in the back and be more continuous. So your top range will be more continuous, your bottom range will be more continuous, and you're going to drive down this variation around 1,000. And that's the magic of doing more than 1 instance, 2 instances, 10, doing 100 instances. The more you do, the more instances you do, the more certain you will get to where the middle is and then what the range of possible values are. Okay. We have 2 more blocks to go before we can hit scenario planning. So let me go through those blocks and then we'll talk about scenarios. Number 1, we need to add parameters to our function. If we don't add parameters, I'm going to have to manually run a giant block of code every time we want to run a scenario. It's much easier if I have parameters in my function that allow me to change this stuff as I run the function multiple times. As I scroll down, you'll see a lot of this is repeat. All of this stuff here, very similar to the manual exercise we did at the top of the R Markdown. This here is that aggregate by arrival function. Right, so you get your single instance, aggregate by the arrival function. Yes, that part of the flow chart I'm understanding. And then I append it to my master data frame. Yeah, okay, so all of this I totally get. I remember the for loop. The big difference here is that if you look at this, OO mean standing for order to overseas port, the average here used to be 14 when we did this manually, even when we had the inner sim function. But now I'm feeding it in as a parameter. So we can run this, I can change my 14 to 13 or 15 or 16, right? And all of these different things within the model that creates uncertainty in our system, we can start to change those and do it pretty quickly once we bring this stuff over to Shiny. As we wrap up this cell, again, I never try to leave the cell without visualizing in some way, whether it's a table or a plot, what the output looks like. So the table looks familiar. It might look redundant, but this is incremental. And then I look at my visualization, and as I scroll down, the visualization looks very similar to what we had above, where we have the line chart around your mean of 1,000 with your gray shaded region. Last step. When containers and container ships start to pile up at the port, or really any backlog state you can think of, it is very unlikely that you will create a backlog and then in a single day, it all goes away, right? If you think about the port, all those ships waiting in the water, it's going to take time to quote unquote clear that backlog because only so many containers can get through the port in a single day or in 2 days. The capacity to process stuff, they're at their max. Everyone, they have all the people they need working, all their equipment is running 24/7, which hopefully we'll get to operating 24/7. There's still only a certain number of containers that can be worked a day. So it's not like if you're the domestic warehouse, you are worrying about this onslaught of volume coming at you. You look at the Wall Street Journal and on the front, you see all those container ships into the water. It's not like that's going to hit your warehouse all at once because it can only make its way so quickly through the port. And we call that, we say, well, the volume is going to get metered through the port. It's only going to come to us incrementally. We need to add that into our simulation. Otherwise, you're going to get results that are just nonsensical. So as I scroll down, I just explained that, right? There's a mechanical max at the port. We still have all of our parameters, but now there's a few things that I add. Number one, I added delay range. And this is where we get almost to scenario planning. So I say anything that arrives at the port between February 1st and February 15th, it is going to be delayed for X number of days. I've added a parameter to the model to specify how many days. Is it going to be delayed 1 day, 2 day, 3 day, 7, 14 days? And then as I scroll down, I have to manage the backlog and I have to meter the volume through the simulation. It's not one line of code. So I'll scroll down and this is the new stuff. So starting here, this is the unfamiliar stuff. This is the new, more complex stuff that I'm adding to the simulation. And I put this on the screen, not to walk through every single line, but I put this on the screen to recall a point that I made earlier about the trade-off between complexity and the ability to maintain your code. So the system that I showed you guys is pretty, is relatively simple compared to reality. I can make it more complex from there to get more granular to what to what real life looks like. But at the same time, I'm going to have to build out this code to handle all that complexity. Now, depending upon your bandwidth, depending upon your resources, maybe you want to do that. But you could also imagine that as you add complexity, you're also increasing your probability of making a mistake. So there's a lot of this that depends on timing and your resources. I'm going to refer again back to what Dr. Price was saying. Sometimes you only have today to turn things around. Sometimes you only have the next week to turn things around. In supply chain and with the ports, the situations are changing pretty consistently. Stakeholders are coming to us and saying, hey, remember we made that decision last week? We need to do it a bit differently. And I need you to tell me if we change this up, can your simulation give me different results? If you have a code base that looks right like this relative to this, it's going to be hard, even if you're very good at commenting, even if you documented everything, you functionalized everything, it's still going to be tough to make ad hoc adjustments like that. I'm not saying don't do it. I'm just saying it's a trade-off. And that's what I have here. So as I scroll down, before I go into delivery, let's look at the last test that I run. So now I'm running sim function, I'm feeding parameters. I'm creating our ribbon data, and now I'm creating our ribbon chart. And the last thing I have on the screen looks very similar to our chart above. Right down here, you have your line, you have your gray shaded region representing your possibilities and uncertainty, but I've also put in the min and max volume represented by dots. So in one of the instances, we had a situation where the arrival volume was above 4,000, but it happened maybe only once in all of our, I think I ran this 100 times up here. So I ran 100 instances to create this chart. And in one of those instances, I doubt two, I think probably one, you had a very high volume here. And then there's also instances where there's a possibility that you get zero volume as a warehouse. And I think this helps, especially in real time, if you're working with planners and people who are trying to work through these scenarios. Hey, Frank, is there a possibility that I might get zero volume? Well, if we look at this output, there is a possibility, but it's really, really small, right? That's an outlier possibility. So the last thing we want to do, and right, tying this back to the title of the talk, is we want to create scenarios. This is all about scenario planning and being able to think with data. And that's what I do here as the last thing. So I repeat, create my delay range, anything arriving February 1st to February 15th. That is going to be delayed by a specified number of days. I have my first scenario here in SimPlan 1 that I call base. You can see I have different parameters, including a delay magnitude, which is 0 days. So in this first one, I'm saying there's no days of delay. And then I have another scenario that I want to compare. SimPlan 2 that I call scenario. Here, I say, what if I had 7 days of delay at the port? What does my volume over time arriving at my warehouse look like? And then I put those together so that I can visualize it. Now I take this, now that we've constructed this whole thing, I take this and I take our function up here and I plop it into a single page Shiny app so that I can sit down with stakeholders and we can think through. So in these last few minutes, let's have some fun. This is a simple Shiny app. You have your levers on the left over here. You have your visualization on the right over here. I start off with 0 variation. So this visualization is corresponding with our base case. I have no variation in my model. So I have just some parameters, not all of them, but just some. My daily order variance is minimal, right? 0.01. That's my standard deviation from a normal distribution with a daily order volume of 100. My transit variance is nothing, right? Remember, I was using the value of 2.5. My days of delay is nothing, and my throughput max is unlimited, right? So you basically can imagine there's no limitation here. But if we start to introduce variance, then you'll start to see a line come up on the chart. So let's introduce standard deviation of 15. Now we have some fluctuation. Now we have our gray bar. Now we have our minimum dots and our maximum dots for our potential expected values. What if we add transit variance? So we get a little more fluctuation in our arrival volume. So let's go with that 2.5. Oh, actually you get a lot. So right, those tails of variance introduces quite a bit of uncertainty. Now recall that I had said we get a lot of spikes here because we're only running 10 instances. And you can see one of the parameters in the model of the app up here is only 10 instances. Let's increase that. Let's go 100. And after a second, the simulation reruns and you can see, okay, so there's a little bit less variance if I do this over time in my average. And then my range starts to fill out around between 800 units arriving and 1,200 units arriving. The next thing we want to do is say, well, what if there is a port delay, right? So in my port delay, in my date delay range, what if everything arriving at the port had a 7-day delay? What does that look like? Let's put in 7. And our volume falls off. Our volume falls off here. So gets stuck at the port. Our volume arriving at the domestic warehouse falls off. It rebounds a little bit to what we feel like is an equilibrium level, and then pops back up to 2,000 units. So now this gets you thinking, oh man, am I gonna have 2,000 units arriving in my warehouse for a week? If so, I need to adjust my labor plan. But remember about metering volume. This might not necessarily be true. What if only 1,600 units can get through the port on any given day? Now this number falls down to about 1,600, but your elevated level of volume remains higher for a longer period of time. So now you have about a little over a week and a half where you have elevated volumes. Finally, we can compare scenarios, right? So the other way to look at this is if we looked at those averages and we started comparing scenarios, what do we see? Now I have one line, which is my base case, and I have another line, which is still at my 1,000. So let's add in that variance that we had above and 2.5, and we'll let it run a little bit. But now your warehouse manager might say, what if you're a worrywart? Like, what if you're worrying too much? What if the delay is only 3 days? And what if the port can handle more than that? What if the port can handle 1,800 units a day? How should I think differently about that? And this is pretty simplistic, but it's interesting because your volume does fall off, yes. And as soon as it reruns, I got to click, enter. Going again. So now, like, because I pressed too many times, we're getting multiple simulation runs. Okay, so my volume does fall off and then it bounces back and it stays at this sort of equilibrium level for a while, and then it pops up to 1,800 per day. And now the question you're getting asked is it really going to be this short-lived? And if so, what is it going to do to my days of backlog? So remember that spreadsheet, right? Do I bring in additional people, or do I run my building longer for this pop? Or can I just work through this and maintain my plan throughout the month? If so, maybe I can just carry a day of backlog into 0.75 days of backlog into a half day of backlog, right? Maybe I don't have to adjust my labor plan if the delay is of this magnitude. If it's of this magnitude, I do, right? So now you get your stakeholders start thinking about different possible futures. And you can think of all kinds of stuff. And when your stakeholders see stuff like this, they will start asking you what ifs, and you will probably go into this cycle where you're going around and around and around, making revisions on your Shiny app. And if that's what you want to do, that's great. But I'm going to use that as the launch point for my takeaways here. So I would increase. I would recommend that if you're trying this stuff out with stakeholders, you probably want to land on your decisions before you start building your system and before you start building your code. If you can land on what decisions might be made with it and the levers that could potentially be pulled, you can minimize the unlimited what ifs that occur after you've built something. Number two, I think the magic here is that framework, that mental model of aggregating those independent instances. And if you can keep that mental model in your mind at the forefront, right, the idea of simulation and the idea of possibilities and probabilities becomes a really natural thought process. I'll say I think it extends beyond supply chain planning and scenario because I think it just automatically gets you thinking more probabilistically about the thing that might happen in your life. Number three, make sure to validate the output every step. I ran you guys through that implementation on purpose. It probably wasn't the most magical thing, but step by step helps you to understand, like, oh man, if I make a mistake at the beginning, that ripples. Like, mistakes at the beginning compound at the end. Domain expertise is just as important as code. I hope I demonstrated that by thinking about the stakeholder, by thinking about the decisions and how the system works and flows. You need to understand that. Otherwise, your code probably won't be representative or even close to what will be helpful to decision makers. And then finally, my last point here is if you want to calibrate your model, you need to calibrate your model. I wrote if you want to calibrate your model, but you should definitely calibrate your model and your models always. That way, when things pop up for stakeholders and they say, hey, that doesn't make sense to me, that I didn't expect that to happen, at least you show them in the past, hey, when we've used this in the past, we've modeled the system flow and it works to simulate the past. So that way, when they see surprises in the future, they won't think, no, the model is wrong. They'll think like, hey, maybe this is a real possibility and I should start to think about how I plan for this. With that said, thanks for your extra few minutes of attention. I really appreciate everyone going on and getting the opportunity to talk through this. I will have the code up on the North 2021 site, so feel free to jump in, grab this yourself, play around with it. Tell me where I'm wrong. I'm here to learn as well. But thank you again, everybody.
All right. Thank you so much, Frank.
My pleasure. Christine, I think you're talking, but you're on mute.
Yep, thanks. I thought I hit unmute, but I didn't. Thank you. Yeah, so we have about 10 minutes before the next session starts. So you can take a break now. Maybe if people have questions, they could, I don't know how much you need a break, Frank. If you have time for a couple of questions, then you could take them. Or if you want to go take a break, then whatever works for you. And maybe people could like email you questions or something if you are able to take them by email.
Both. I'll hang out for the 8 minutes we have, or the 10 minutes we have here.
Okay, awesome. Thank you.
Thanks.
All right, and then also I put in the chat like the link if you want to return to the other session for Dr. Carrie Tribble's A Picture is Worth 3.7 billion years. And then otherwise we have Dr. Eric Daza in this session in 10 minutes. Okay, thanks everyone. Thank you so much, Frank.
Thanks, Christina.
And also we do have a few questions in the chat, Frank. So if you want to look at them now, you can certainly do that.
Looking, okay. Do you know the pros? So anyone's still on, do you know the pros cons of your approach versus using a package like Monte Carlo? So man, I'm gonna, right, first question I'm reading here, I don't know. I haven't used a package like Monte Carlo. When someone taught this to me, this is the approach we took. And that person was my peer at Target. They were, I've learned this stuff. I felt like they were an expert. So when we were building stuff within Target, right, that's really the approach that I took. I could imagine one pro of doing it this way is you have more control versus using the package Monte Carlo. But at this point, right, I don't know what the cons are. I probably will now explore the Monte Carlo package. I'm reading this question. Do you have a process for checking the actual volume and adjusting your assumptions or model based upon that? So I think that's the last thing that I had mentioned, right? Calibrating your model, like any good machine learning project, you have your train set, you have your validation set, you have your test set. I think the same thing applies here. Although the uncertainty in the future and the things that possibly change in the future, I actually love Monte Carlo because things that are happening now, in some way, shape, or form, you might argue that they did happen in the past, but things are pretty brand new now. And then if you open up, so one of the things that Walmart is starting to do is, this is the wrong word, but I keep saying commandeer smaller container ships. And they're putting all of their containers coming from overseas on smaller container ships so they can bring it into smaller ports. And they don't have to hit LA, Long Beach. They don't have to hit Seattle or Norfolk or Savannah. They could bring it into Portland or Oakland because those ports can handle those ship sizes. And right, that hasn't happened before. So yeah, haven't done this, but I like to see the steps and understand the process. I think it is a, again, I like thinking through systems. I like systems thinking. I feel like this is one of those data-driven methodologies that really forces me to think through systems. So I agree with you, Ben JL. As well, communication is key. The Shiny app, for sure. I wish I would have, if I was doing this again, I probably would have cut out some of the implementation stuff and had more time to explore scenarios in the Shiny app. Reading your comment, Christina, I agree with Frank on that. I personally like to code things myself because it gives me a lot of flexibility to code exactly what I want. Yep. I love this one. PS, so someone messaged me in the background talking about logistics in the armed forces, and sometimes things change like that, and you have to make a decision. Which I out of all the courses I've taken and all the work I've done in data and analytics, I think probably the most, still unfortunately, like the most underappreciated thing is the translation from model to action, which is why I dubbed my group Decision Intelligence. So I, at Target, kind of force my stakeholders to think about starting our conversations with decisions rather than I need this Metrica report. Yeah, Monte Carlo was always an absolute mystery to me, sort of still is, but I'm getting there. And then Chase, you asked, how do you discover other factors influencing your model, such as increasing frequency or more severe storms, introducing more route type delays? So I think that's a matter of going back to the drawing, right? The quote unquote drawing. I simplified my reality here, but I think you add those things into your drawing. And then the part that you don't have is historical data. If you don't have the historical data, like how do you model that stuff? I think that you do what Dr. Price was talking about earlier, and sometimes you have to make your best guess. Sometimes you have to take a distribution of something similar, use that as a distribution, and see what values you get, and be clear with your assumptions. Right? Sometimes I think a lot of the COVID stuff that we saw over the past 2 years, as a data person, I love the stuff coming out, especially the stuff that was kind of put on the screen. Hey, this isn't meant to scare you. This is meant to make decisions. We're not trying to say we know what the future looks like exactly, but this is one possibility. And I think if you're trying to add components to your model, you just need to be clear with how you're doing it and how you're thinking about it. In my experience, my partners they found that incredibly refreshing, because there's the possibility of saying like, the data doesn't exist, I can't do it. We've never done that before, so it's impossible to find out. I do say that same thing, but at the same time, I say, let's think about something reasonable and use your intuition and experience and business logic and see if we can come up with a reasonable estimate. So you guys can hear me, assuming you're still on. I can't hear anyone. So hopefully, Chase, that gives you some ideas.
And if anyone had any other questions that they wanted to speak aloud, you can raise your hand and I think I can unmute you. Otherwise, we have a couple minutes until the next session starts, and we could take a break as well. And I'm not seeing any hands at this point. So I'll say thank you to Frank, and everyone feel free to clap your hands or your real hands on video if you want, and thank Frank along with me. The next, the next presenter in this room will be presenting Stories from Biostatistics to Health Data Science. That is Eric Daza. I will post that in our chat here, as well as the link if you want to see the other room presentation. That is A Picture is Worth 3.7 Billion Years, Showing Evolution in R by Carrie Tribble. So I'm going to post that link. Let's see. And yeah, feel free to bounce back and forth. We'll take a break here for a couple minutes and we'll see you back at 11:30.